All right, we're going to go ahead and do an example of related rates. Now, this is the example that involves a snowball. Now, this snowball is melting at a rate of pi feet cubed per hour. At the moment when it is 30 inches in diameter, we want to determine how fast the radius is changing. So that's one part of this question, and how fast the surface area is changing. We're going to use my suggestion of this little acronym here, the SREDWOO acronym. We're going to sketch a picture, write down the rates, the equations, take derivatives, plug in the when values, and make sure we write our answer in units. Okay, now let's think about this a little bit. One of the hardest parts of related rates problems is figuring out what equations to use and what's kind of going on. That's why we do these first two steps, sketch and rates. The sketch for both of these part A and part B parts of the problem is going to be the same. We've got a snowball, which we're assuming is a sphere, that has a radius r and a diameter d. We're told something about the diameter, but a lot of the equations that involve spheres often involve the radius, so I gave that a name. Okay, so let's start with how fast is the radius changing when the snowball is 30 inches in diameter. Okay, so part A here. We did our sketch. Now we want to write down our rates. Usually when I think about writing down the rates, I ask myself, what am I told and what do I know? What we're told is that the snowball is melting at a rate of pi feet cubed per hour. What we want to know is how fast is the radius changing? When you see the words how fast or things related to that's like a rate. We want to know the rate at which the radius is changing. So we're told this rate in the problem, and I want us to take a look specifically at the units here. The units are feet cubed per hour. Now, the quantity that involves shapes that uses a cubed unit is typically the volume of that quantity. So this is telling us that the volume of the sphere is changing at a rate of pi feet cubed per hour. So we're sort of told a time frame as well. Okay, so I'm gonna give the volume a name. I'm gonna say it's called V. So V is gonna be the volume. And we're told something about how the volume is changing. We're told about volume per time. So that means I know that dV dt, that's volume over time, so the change in volume over time, has something to do with pi feet cubed per hour. We're also told that this snowball is melting, which means that it's getting smaller. So that means that the rate at which the volume is changing should be negative because the volume is going down. If we left this as positive, it would tell us that the snowball is actually getting bigger, which kind of doesn't make sense unless it's maybe snowing and then maybe the snowball's accumulating snow. But that's not the situation here, it's melting. Okay, so this is one of our rates, the volume. We want to know how fast the radius is changing. That's dr dt. That's what we would like to find out. So we've done the sketch part of our acronym. We've written down the rates that we're interested in. Now we need the equations. We're going to take a look at the rates we have here and just the variables that are involved. I have a volume and I have a radius. So I'm going to write down an equation that involves the volume and the radius. Okay. The volume of a sphere, capital V, is 4/3 pi r cubed. That's a formula for the volume of a sphere of radius r. And notice that that relates the variables v and r, the variables that we've been talking about for this part of the problem. Okay, so we've done that part of the acronym. Now we're going to go down to derivatives. Derivatives. I need to take the derivative of this expression with respect to time. So I'm going to compute derivatives with respect to time. Okay. So I'm actually going to need to do implicit differentiation, meaning that wherever I take derivatives of variables that depend on time, like volume and radius, I'm going to write d variable dt next to that. Okay. So the derivative of this of v by itself, it's got a power of 1 up here. So really the derivative of this is 1. But so it's like 1, and then I need to write down dv dt next to it because it depends on t and I'm taking derivatives with respect to time. Then I need to take the derivative of this expression. 4/3 and pi are just constants. So really I need to compute the derivative of r cubed with respect to time. That's a power rule. The 3 comes down in front, and then I do subtract 1 in the exponent. So I have 4/3 pi times 3r squared. This is the derivative of r cubed there. But because I'm taking derivatives with respect to time, and r sort of secretly depends on time, like the radius is changing as the volume melts, as the snowball melts, I have to write dr dt next to that. Okay. All right, so now I'm going to look at the when. The when step of this process is once we have our equation or our differentiated equation, I want to know something about this when something happens. And oftentimes the when is in the question. When the snowball is 30 inches in diameter. Okay. So let's take a look first at the things we know. The when step means we want to start plugging in numbers. Okay. The numbers that we know are dv dt. Remember, we had that way up here. dv dt is negative pi. So I'm going to go ahead and, so here I've got dv dt 4/3. I'm going to multiply some of this out, like simplify this a little bit. Notice that I have 4/3 times pi times 3. This 3 up here and this 1/3 here cancel each other out. They multiply to 1. So this is 4 pi r squared dr dt. Now I know the value of dv dt from way up here in our first step. dv dt is negative pi feet cubed per hour. What I'm trying to find is dr dt. So there's nothing for me to plug in there. That's what I'm going to solve for. My final answer will be dr dt equals some number. The only other thing I need to be concerned about here is this r. I need to plug in a number for that. And we can plug in a number for that. It's just not quite in the form we want it yet. What we know is that the diameter is 30 inches. So I need to convert that to a radius. So we know, dv dt is negative pi. We know the diameter is 30 inches, and I should say this is negative pi feet cubed per hour. Well, the radius of a sphere or a circle is the diameter divided by 2. So we really want to know what's going on when the radius is 15 inches. We can't quite plug in 15 for this r though, just yet, because we need to make sure all the units match up. Here, volume is in feet cubed per hour, but this radius is in inches. So I need to convert this inches to feet so that I can plug in all the numbers. I can't plug in 2 different length values here. So I'm going to, you could think of it as multiplying. I sort of need to like cancel out this inches and be left with a foot unit. So for every 1 foot, there are 12 inches. And I know that I need to divide by the 12 inches because I need to like cancel out that unit. So really, the radius is 15/12 feet, which is 5/4 feet. Now I can plug 5/4 in to that r value. Okay, so let's substitute the values in. I have negative pi, that's feet cubed per hour, equals 4 pi times 5/4 squared dr dt. Just as a reminder, this was dv dt. This was 4 pi r squared, and then dr dt is just hanging out here because that's what we're trying to solve for. All right, so now I need to, the original question was how fast is the radius changing? So I need to solve for dr dt. All right, all this stuff is getting multiplied. So I just need to divide by this expression. If you'd like, we can maybe simplify this a little bit here. So let's simplify. We've got 4 pi. 5/4 squared is 25/16 dr dt. And then I have a 4 over a 16. Well, 4 goes into 16 4 times, so I can replace that with a 1 and that with a 4. So really I have negative pi equals pi times 25/4 dr dt. Okay. Now I'm going to solve for dr dt, which means I'm just going to divide by this. This is just a number, right? It's 3.14 blah, blah, blah times 25/4. That's just a number. So I'm just going to divide this whole big thing over. I'm going to divide it on both sides. So divide by pi times 25/4. Divide the other side by pi times 25/4. Oops, I wrote that wrong. Okay. I wrote that totally wrong. I'll write it right when I actually write it down. So I have dr dt equals, I had a negative pi over here, and I'm dividing by pi 25/4. Okay, let's simplify things a little bit. These pi's can cancel out to 1. And when you divide by a fraction, we need to multiply by the reciprocal. So flip it over. And just remember we have this negative here, so don't drop that negative. Or negative 4/25. Okay, and just to write this a little cleaner, I have dr dt equals negative 4/25. And the last step of that acronym, let's go back up here, is the units. I need to make sure my answer has the right units. Let's go back down here. The units of dr dt, well, the radius is in feet, and the time t is in hours, so this is going to be feet per hour. And that is our answer for part A. The radius is changing at a rate of negative 4/25 feet per hour. It's getting smaller. Okay, we're going to move on to part B. I'm going to copy the question over just because I feel like it's going to be helpful. And maybe our sketch, why not? Roll all the way down. Let's do part B here. I'll move this up a bit. Oh, hold on. Sorry, I'm having trouble grabbing the picture there. Okay. And let's make sure I have enough pages to do this. Okay. We did this one, check. Now we're on part B. How fast is the surface area changing? And this is at the same point in time. So when the diameter is 30 inches, which we decided that was when r equals 5/4 feet. We decided that's the same as the diameter being 30 inches. Okay. We still also have dv dt equals negative pi. I don't know if we'll need it, but we've got it. We actually might not need it in this point, but why not write it down? Okay. What we also have too, we just found in this other problem, is that at this moment in time, dr dt is negative 4/25. Those are all the quantities that I know of at this point in time. We already have our sketch. We want to write down our rate, so I've written down a few, but we're also asked, how fast is the surface area changing? So maybe ds dt for surface area, or you can use dA dt if you want to use for area. How fast is that changing? That's what we want to know. So this is what we want to find. Okay. Well, I need a way to relate surface area to some of my other variables that I have here. It's not going to help too much to relate it to volume. I mean, you could. There's a way to do that, but maybe the simplest approach is maybe if I just write down the equation for surface area and see if that helps us out at all. So here I'm at the equation stage. Okay. The surface area of a sphere is 4 pi r squared. Now this equation relates surface area, great, with radius, and we have information about the radius, so this is a good equation to use. All right, then we need to take derivatives, again, with respect to time here. So wherever I take a derivative of something that depends on time, like the surface area or the radius, I need to put the d variable dt next to it. All right, the derivative of s here is 1, and then I need ds dt next to it. 4 is a constant and pi is a constant. So when I take the derivative of this expression, I can just pull the constants out front and I take the derivative of r squared. So I have 4 pi times the derivative of r squared is 2r. But again, r depends on time, so I need to write dr dt next to that. Okay, so really I have 8 pi r, dr dt. At this point, I'm at the when step. So I've taken all my derivatives. I'm at the when step. The when means plug in values. So what I wanted to know was what's ds dt. And I know that it's equal to 8 pi r dr dt. So I need to plug in a number for r and a number for dr dt. Well, I already know that r is 5 over 4. So I'm going to plug 5 over 4 in for r. And I know that dr dt from the previous part of this problem is negative 4 over 25. So I'm going to plug negative 4 over 25 in there. So I have 8 pi times r, which is 5/4, times negative 4 over 25. And we just can simplify this a little bit. These 4s, I'll write that a little better. These 4s cancel out. 5 goes into 25 5 times. So I've got, I don't know why I did this whole problem in green pen, but hopefully that's okay. I still have 8 pi out front here, and then I have times negative 1 over 5, looks like. All right, and then I can still make this look a little bit cleaner. So I could write this as just negative 8 pi over 5. And then remember our last step is the units. The units of this quantity are going to be area over time. Now, like I said earlier, volumes have like a length, a distance or a length cubed. So feet cubed is a volume. Area is going to have units of like a squared length. So area has units here of feet squared. And this is over time, and time here is in hours. Okay. So if I write this a little bit cleaner, I'll say ds dt is negative 8 pi over 5 feet squared per hour. And that's my final answer for part B. Hold on, I want to make it look like a nice rectangle. Okay. Okay, that's the end of this example. Please let me know if you have any questions.